I'm Judy Hill. I'm the group leader in the scientific computing group at Oak Ridge National Laboratory. And the group that I work in, or that I lead, is tasked with working with Summit and with Titan. Who all has heard of Titan? Has everyone heard of? All right. Who all has heard of Summit? Okay, I'll just quit now. You don't need my talk. No. So today I want to give you a little bit of an introduction to both Titan, but we'll spend most of our time talking about Summit, some of the things that we've learned already, even though it's not really available to you all yet. Okay, this isn't that. There we go. So what are we going to talk about today? So I want to talk briefly about the OLCF's roadmap to exascale, and I do want to preface this by saying that Scott Parker and I did not collaborate on our talks, but they look somewhat similar. Towards the end, I'll deviate a little bit from what he did, but I'm going to talk about a little bit different architectural path toward exascale. Then I'm going to give you some information about the Summit architecture specifically, talk a bit about some of the programming considerations you might make for heterogeneous systems. I think this will dovetail nicely into a lot of the talks you're going to hear later in this training session. So we won't go into much detail here, but I want to give you a flavor of the types of things that me and my group think about as we're programming these systems. And then I'll have a couple of slides on early application results, because I think we're mostly applications people here. So I want to give you a flavor of what we think Summit's going to be able to do based on some of the early work that we've done. And we have to do that all in 25 minutes. So, not sure we'll get through it all, but the slides are available on the website, or will be available on the website shortly. And I'm here all day until later this afternoon if anyone has specific questions or wants to talk about anything. The other thing is, I am perfectly fine if people have questions, if you want to interrupt me during my talk. That's fine with me. I'd rather we go more slowly through the material and really understand it rather than trying to get through everything, because I know it's a lot to talk about in 25 minutes. Okay, so Scott briefly mentioned what the leadership computing facility is. Now, it's actually a single facility operated both at Argonne and Oak Ridge. And we're here to solve the largest problems in science, really. Really think about any problem you might have in science, from astrophysics at the very biggest to nuclear physics at the very smallest, and everything in between. We field some of the largest computers in the world, and we have some of the best computational scientists in the world. In particular, at the OLCF, our mission is to field those most powerful capability machines. Argonne has the same. I don't want to make you think that this is only the OLCF mission. Argonne has the same mission as well. We field the most powerful capability machines in the world. We build the required infrastructure. Scott touched on that a little bit this morning. I'll touch on it a little bit this afternoon. All the infrastructure required to field these machines. We select a very few time-sensitive problems of national importance to solve, and we partner with these teams that use our facility to make them as efficient as possible, so we get the most science out of those machines as we possibly can. That's really where my group comes in. We partner with application scientists every day on Titan, and eventually now on Summit, to make their codes as efficient as possible and to collaborate with them on their science problems. So if you look at the path toward exascale, this has been a long path, and it's an evolving path. It actually goes back to 2008. Oak Ridge fielded a machine called Jaguar. It was a 2.3 petaflop machine, entirely x86-based architecture. At the time, it was the world's fastest. And then there came this architectural change, or architectural evolution, as you might say, when we fielded Titan in 2012. Titan is a 27 petaflop machine. It was the world's first very large accelerated computer. And at the time, it was the world's fastest computer. If you look at what we're fielding today with Summit, it's about 10 times faster than Titan, really more like 7 times, still on this accelerated computing pathway. And we expect to get 5 to 10 times the application performance as we see today on Titan. If you look ahead into the future, we're already thinking, even though Summit's not here for you to use yet, we're already thinking about what that exascale machine might look like. We're calling it Frontier. We expect it will be an exascale, exaflop or greater, and we're right in the middle of a competitive procurement. We hope that it will also be 5 to 10 times the performance that we get on Summit. I can't really say much more about Frontier at this point, but I think if you look at this pathway, you can see that we've been very concerted about how we've made our choices so far. So I think to understand the Summit architecture, we really have to go back and look at the Titan architecture. And I'm pleased to see that you all are familiar with Titan, but in case there are a few people who are not, this is what Titan looks like. So I'm from Tennessee. Well, I'm not really from Tennessee. I live in Tennessee. I'm from Kansas, so I really don't have much over Tennessee either. Being from Kansas, though, I also believe in basketball. If anyone is a Jayhawks fan, if anyone is a Duke fan, don't talk to me. No, I'm kidding. I'm kidding. So if you look at a basketball court, I have to make it orange, but I'd like to make it red and blue for the Jayhawks. This is effectively what the size of Titan looks like. It's about 4,300 square feet. It's effectively, when you add the disk in addition to the compute nodes, it's effectively the size of a basketball court. If you've never had the opportunity to tour one of these machine rooms, I highly encourage you to. It gives you a different perspective on the computing power that we have. As I said, it has a peak performance of 27 petaflops, operated over almost 19,000 compute nodes, each node of which has a 16-core AMD Opteron CPU and an Nvidia Tesla GPU. There are 200 cabinets, 200 racks of computers that make up Titan. And Titan today consumes, at its peak performance, about 9 megawatts of power. So go back to what Scott was talking about a megawatt being about $1 million. That gives you some idea of what our electricity bill is every month. It's not small. That's why we're so focused on getting as much performance out of Titan as we possibly can. So I want to, as we look at the Summit node architecture, I thought it was important that we also look at the Titan node architecture. So as I mentioned, so this is actually 2 Titan nodes here. So let's just look at this one side. In Titan today, we have a AMD Opteron core, which is a 16-core processor, typical x86 processor that operates at 2.2 gigahertz. Sitting off of the CPU is 32 gigabytes of host memory. And also sitting off the CPU is an Nvidia GPU, a K20X, which has a peak performance of about 1.31 teraflops. Off of the GPU memory, there's GPU memory that's about 6 gigabytes. So if I look at this schematically, and we're going to look at a Summit node here, we have the x86 core with memory bandwidth of 51 gigabytes per second to the CPU memory, a PCI Express bus over to the GPU with its 1.3 teraflops. That PCI Express is 6.4 gigabytes per second. And then this what I would call today high bandwidth memory, this GDDR, operating at 250 gigabytes per second. So here's my question to you. First question of the day. As an application developer, what pain point do you see with Titan? It can be in the node architecture, it could be in the system architecture. Any thoughts? Yeah? PCIe, absolutely. Anybody else? There's no wrong answers here, and every application may give a different answer too. Any other challenges?
Small onboard memory for the GPU.
At the time, it was big. Today, it's small. Yep. Anything else?
Different instruction sets.
If you get down deep in, yep, absolutely. Anything else? It's not on this slide, the sheer number of nodes. Nearly 19,000 nodes is not easy to program for. Anything else? So all of these are correct answers. As an application developer, the biggest challenge that we have found is this PCI Express bus right here. Most of our applications are limited by this network right here. I like to think of it as I have a really fast GPU sitting here with about the tiniest straw to get data back and forth between the CPU host memory and the GPU. So you have to think very carefully about how you program this. So coming soon, real soon, is Summit. It's going to replace eventually Titan as our leadership computing, our leadership computer at the OLCF. Titan will be in production. We plan until the end of next September. So we still have another just over a year of Titan. Summit will go into production in January. The most exciting news about Summit recently is on the June Top 500 list, Summit was named as the #1 supercomputer in the world based on the LinPack performance. It achieved 122 petaflops per second of its 200 peak performance. So that was pretty exciting. Not nearly as exciting as all the science that we're going to be able to do out of it. So if I compare Summit to Titan, what are some of the differences in the architecture. So in terms of application performance, we expect 5 to 10 times the application performance of Titan. Realize that the peak performance, peak-to-peak comparison is about 7. As we get into the applications, early application results, you'll see that we're actually getting more than 7 in some applications. In terms of the number of nodes, on Titan we have this nearly 19,000. On Summit we're going to have 4,600 nodes. So I'm getting 200 petaflops with a quarter, 7 times as much performance with a quarter as many nodes. So what does that mean? I have a really, really powerful node. I have a 42 teraflop node sitting there compared to just nearly 1.5 teraflops on Titan. That's a whole lot of flops to take advantage of. In terms of the memory per node, because of all of these flops, it has 512 gigabytes of CPU RAM and 96 gigabytes of high bandwidth memory. Yeah.
So you show that Summit reached about 60% of the peak performance with the impact benchmark.
Yeah.
How does Titan compare to that?
17 over 27, roughly. There's some decimal points in there, but if you can do that math, that's the number. Okay? Yeah, it's not too different. It's about 60%, yeah. Okay. So in terms of the memory per node, it's going to be an extremely fat node with a lot of memory available and with some NVRAM also sitting off each node. We'll have a 1.6 terabyte SSD hanging off each node. So in terms of total system memory, compared to Titan where we have not even a petabyte of memory, we're going to have over 10 petabytes of memory by the time you include that entire hierarchy. In terms of the interconnect, Titan has a Gemini interconnect. We're going to have a dual rail Mellanox EDR that's about 4 times as fast as what's on the Titan interconnect. In terms of the processors, so as we mentioned, there's a single AMD with a single GPU. On Summit, there's 2 IBM Power 9s with 6 Nvidia Voltas hanging off of them. The file system, if you're doing lots of computation, you have to have a place to put all of this data. We have a 250 petabyte file system with bandwidth of 2.5 terabytes per second into it. Now, what I think is one of the most exciting things about Summit, as I mentioned, Titan consumes about at its peak, should consume about 9 megawatts of electricity. For 7 times the performance with Summit, it should consume at most 13 megawatts. So for a 50% electricity bill increase, you get 7 times as much performance. That's one of the reasons why the OLCF has gone down this pathway, is simply because the electric bill is going to be too expensive otherwise. So Scott presented a similar graph for Theta, and so I thought I actually had this in already. So if I look at the compute system of Summit, it's going to have 256 racks for 4,000 nodes. It's going to look something like that. I'm just giving you interesting factoids. For each compute rack here, one of the interesting things about Summit, this is the first time we've gone with a warm water cooling system. And for mechanical engineers, that's a really innovative solution. So Titan is water cooled as well, but it's chilled water. So today with Summit, we only have to have 70-degree water, which is much warmer than what you would find in most data centers. Also contributes to some of the electricity savings. I think we've talked about the rest of this, and I'll talk very briefly about the Nvidia GPU brief in a second. In terms of the IBM Power 9, it is a 22-core architecture. I'm not going to say much more about it. I can talk offline if you'd want, but I've got 10 minutes left and a lot more material to cover, a lot more interesting things. So if I look at the Summit architecture compared to the Titan architecture, as I mentioned, we have 2 P9s sitting here. They're connected by a 64 gigabyte per second bus. They each have 256 gigs of DRAM sitting off with bandwidth of 170 gigabytes per second. And they each have 3 GPUs sitting off of them, connected to the P9 with 50 gigabytes per second into each GPU, and each GPU is connected to each other with bandwidth of 50 gigabytes per second. This is NVLink, if you're familiar with that terminology. Each GPU has 16 gigabytes of high bandwidth memory sitting off of it that operates at 900 gigabytes per second. In terms of the network connection into other nodes, there's 25 gigabytes per second into other nodes, and then here's this NVRAM sitting off of one of the P9s. So as you look at this node architecture, question number 2 of the day, what are the pain points here for application developers? Yeah.
Orange arrows.
Okay, into the NIC. That wasn't intentional, so that's intended to be PCI, but absolutely, particularly this one right here. It's not really orange, it's brown. That network connection. Yeah. Anybody else?
The GPUs are not connected on one set and the other set?
Absolutely. So if you are using multiple GPUs and you need to get data from here over to here, you have to go through, they're not connected directly across there. And we'll see in a second some NUMA effects for that. Yeah. Yeah.
16 gigabytes is still very little for 7 teraflops.
The memory per flop is still challenging. You're absolutely right. Anything else? Yeah.
So can you explain why crossing across is bad? Because the connect between the P9s is higher bandwidth than the 50 gigabytes for each graphics card already.
So there are still NUMA effects, and we'll see it. So I think by looking at the architecture, you're absolutely right, but hold that thought, okay?
In terms of programming, there's increased on-node parallelism, so you need to manage data transfers explicitly, I guess.
You don't have to manage it explicitly. There's a slide about that in a little bit. So you can manage it implicitly, or you can allow the system to manage it implicitly. I will say that our high-performance users, our big iron, getting close to the metal people, always want explicit control. Yeah. There's a performance penalty often to be made when you allow the system to do things for you. Yeah. Anything else?
The NIC is not connected to the GPU.
The NIC, right here? Yep, you're absolutely right. So the other thing I would say about this node compared to the Titan node, this is a really complicated node. There's a lot going on here when you compare it to what that Titan node looked like. It offers a lot of possibilities, but I think to really get performance out of this thing is going to take a lot more work than even the Titan node takes today. Okay, went too far. Here we go. So as I look at, going back to some of these ratios between things, where are the pain points? So if we look at the high bandwidth memory, bandwidth compared to the CPU bandwidth, Titan actually looked pretty good. If you compare this 51 gigabytes per second from the CPU to the CPU memory versus the 250 gigabytes per second to the GPU memory, it's not perfectly balanced, but it's pretty darn good. But here's where the real win comes on Summit. It's the high bandwidth memory, this 250 gigabytes per second, versus getting it over to the CPU. That's where Titan, we identified that a few minutes ago, that's where Titan was the real pain point. And so you can see it's much more balanced for Summit. It's not one-to-one. It's not perfect by any stretch of the imagination, but it's a whole lot better. In terms of the memory capacity, to gigaflops or to petaflops. If I look at the total memory available on this node to the total performance, the number of teraflops per available, it's 0.01 compared to 0.03. So we are in an even more memory-starved environment today. Flops are free, memory's not. So worrying about where your data is and how to get it to the right spot is the thing we probably worry about the most. And the other challenge is if I look at the injection bandwidth, so if I look at the network speed out to other nodes versus gigaflops, we are in a network-starved environment as well. So keeping track of where your data is, using it as much as possible, and trying to avoid moving it, if at all possible, was true for Titan. It's still true for Summit. There is no free lunch. Even with this great new architecture, there are still a lot of things to be worried about. The win, though, flops to power. 15.4 flops compared to 3 for Titan if I look at the power efficiency. One thing I do want to point out, there's a reference here, and this is on the last slide also of the PDF that's available for you. This is an SC18 paper that looks at a lot of the details we're talking about today in even more depth. So I encourage you to download it or to, once it becomes available for SC18. Yeah?
Just to make sure I understand, is that supposed to be G flops at the bottom maybe, or is that 15.4 flops to a megawatt?
It's not 15.4, and it's probably petaflops. I don't remember. I wasn't very careful there, was I? Yeah. There is a ratio. If you divide something, you'll get this number, but I'm going to have to go back and look at it. I realize that too. It's not flops per megawatt. That would make a really expensive power bill. Okay, so let's look, in the few minutes that we have left, let's look at a few of the benchmarks, things that give you an indication of where some of the challenges might be. So if we look at the stream benchmark, this is a very simple synthetic benchmark that measures the achievable memory bandwidth using OpenMP threading. So if I look at the DRAM bandwidth, this is measuring how much of that peak bandwidth I might actually be able to achieve. This gives us a measure of kind of that upper bound. So on Summit today, we expect this 170, I'm measuring what fraction of this bandwidth here I might get. So the maximum is 340. We're getting about, if I look at the stream benchmark, these are 4 different operations available, we get about 82% of that peak memory bandwidth, compared to Titan, which only gets about 67% of the memory bandwidth. So this is one of those architectural improvements that even though the bandwidth ratios themselves, are better, we're even getting a higher fraction of those theoretical peak bandwidths. If I look at the same thing on just looking at the GPU, I get 92% of that 900 gigaflops. So I'm looking at this bandwidth right here. How fast can I get data in and out of the GPU from its high bandwidth memory? On Summit today, we're getting about 92% in this idealized synthetic benchmark, versus on Titan, with the same benchmark, you only get 72% of the peak. So the bandwidths, we're achieving more we're getting more of the fraction of the peak. For these tests on Summit, they were actually done on Peak, which is 1 rack of Summit, a test system. These were the best results in 1,000 tests. There is variability, so don't expect that you'll always get these type of numbers, but that variability is up to about 9%. So in terms of the Nvidia Volta, there's one thing I want to point out to you. There's lots of details on the web about the specs of the Volta. The thing that's most interesting to us in the scientific computing group that I actually don't have a good answer for you yet is this introduction of the tensor cores. So the tensor cores are a mixed precision core. They're really a half precision core that give you 16-bit matrix multiply and add operations and then accumulate in single precision. This is new to us. This is something new with the Volta that we didn't have on the Kepler, and we're still learning how to use this. But my message to you is mixed precision algorithms are something that I would highly encourage each of you to start looking at to be able to take advantage of these. I think I'll leave it at that for this one. In terms of the NVLink bandwidth, if we measure from core 0 to so here I'm trying to understand what the bandwidth is of those connections between the GPU and to the CPU. So if I look at hosts, so the CPU from core 0 on a CPU to each of the 6 GPUs and try and measure that bandwidth, it should max out at 50. So if I'm at core 0, what I wanted to point out here is the NUMA effects. So core 0 or GPU 0, 1, and 2 get about the same bandwidth if I just look at core 0 to each GPU individually at about 45. Cores 3, 4, and 5, this goes back to the NUMA effects that we're talking about, really get about 90% of what the close GPUs get. So there are still NUMA effects to be considered with this architecture. This is not a use case we expect most people to use, but it gives you an indication that if you're going across that bus between the 2 CPUs, there's still a performance penalty to be had. These are available on the slide, the PDF. I think I want to skip through them because a lot of these are very similar to what we just talked about, and I was just pointing out essentially NUMA effects for all of these. So the message. Summit's in pre-production, so unfortunately, I don't think you all get to have access these 2 weeks to this machine. It will be available to the general user population in January is our expectation. It's going through acceptance right now, and if anyone's not been through an acceptance of one of these bleeding edge machines, you always encounter things you never expected. We hope to have Summit accepted by the end of September, and then it will be in what we call early science for early access users for about 3 months, and it will go into the general user availability in January. At that point, with a small proposal, a director's discretionary proposal, most anyone can have access to it. I think what I want to do is skip through and talk very briefly about, as application developers, what you might want to be thinking about in terms of programming this kind of architecture. And we've talked a lot about these type of things. So there are lots of different ways to program on this architecture. A very simple model is going to look like Titan, and we'll talk about that in just a second. Additional models, we already talked about this. You have to expose as much node level parallelism as you possibly can to efficiently use this architecture. There are other low-level ways to program on Summit. Our team, our application development team, we actually don't recommend that for most people. If you're trying to extract every last flop you possibly can, then it might be something we want to talk about. But you're probably sacrificing something else like portability to other architectures. So that is something we would say use with caution. But the key is expose more node level parallelism. So in terms of how most people are thinking about using Summit, they're actually thinking about using it very similarly to the way that they would program Titan. They're thinking about having 3 MPI ranks sitting on one socket, 3 MPI ranks sitting on the other socket, and each one talks to an individual GPU. If you want to use more of these CPU ranks, if you have some inherently serial operation that can be done on the CPU that doesn't make sense to transfer to the GPU, you can use OpenMP Threads, you can use Pthreads to really efficiently exploit these CPUs. But one thing we would caution you, the CPUs are a really small percentage of the flops compared to those GPUs. So what are the pros of this? This is really straightforward. If you're already on Titan, most applications, I don't want to say compile and run. There's lots of optimizations to be done, but you can take advantage of Summit fairly quickly this way. One of the cons of this approach, though, is you're possibly leaving some Power 9 cores sitting idle. Remember, there's 22 cores sitting on each of these 2 CPUs. You might be leaving some idle. I don't know that I care. Given that most of the flops sit over here in the GPU, that's something that's application dependent and you have to think about. We do have some people that are using a single MPI rank to all 6 GPUs or some other fraction rather than 1-to-1. Probably the most common is this one, having one MPI rank sitting on one socket and the other on the other socket talking to these 3 GPUs, and then using OpenMP down here. You can use threads, you can use language constructs, you can do all sorts of things to manage it this way. This is another use case that we expect to see. I'm going to talk about one application, and this is not my application, but this is one of the new use cases for Summit. So we like to talk about Summit being the smartest supercomputer in the world. We see with those tensor cores, we see great availability or great potential applications for machine learning and AI. And this is actually a genomics project that's being led out of Oak Ridge by Dan Jacobson, who's a genomics person, and Wade and Jobert, who's an application scientist in my group. The key here is that these tensor cores, they were able to already achieve what we call an exa-op. We're not calling it an exaflop, but using those half-precision cores on about 4,000 nodes, they got an exa-op just over 2,000 nodes, and are projecting, with 4,000 cores, they got 1.88 exa-ops. That in and of itself is not very interesting. What is interesting is that by doing some algorithmic improvements, they were able to do things on Summit 4.5 times faster, Summit to Summit, by using the tensor cores. It shows you some of the power of this new feature that we're just now learning how to take advantage of. They got 80 teraflops of mixed precision per GPU for their entire application. If you just look at the cuBLAS performance, they got over 100 teraflops, and that really probably ought to be teraops. So they're getting huge gains out of these GPUs, primarily coming from the tensor cores. So there's lots of opportunity for figuring out how to make efficient use of Summit. We've only scratched the surface. So I encourage you, as you all are here for the next 2 weeks, listen to the details of these architectures, figure out how to exploit them. There's lots of opportunities. This architecture it's not incremental, but it was the next step in the accelerated pathway. But there's still lots of things that we can do to take advantage of it. With that, I will stop. I do want to acknowledge my entire team who helped put this talk together. Here's that site for that paper where a lot of these results came from. And then the other thing I'll mention is there will be Summit training at Oak Ridge, tentatively scheduled for December and February. And these are typically also broadcast. So if you're not able to travel to Oak Ridge, we encourage you still to sign up and watch via webinar, where we'll have a lot more detail about how to actually use Summit on that. with that, any questions while we transition?
So, since these GPUs which are attached to Summit are quite powerful, I imagine they also chew up some good amount of power. Is there any way to sort of toggle the power in such a way so that if only the GPU is active for the portion it does some computation?
So the GPUs are really good about powering down when they're not being used. So what I presented on that 13 megawatts was actually peak power. If everything was running full throttle, we're not measuring it at that level 100% of the time, not even close. So they're very good. They're known to be energy efficient for that exact reason. Yeah. Anything else?
The system, the previous you have talked about used one single GPU per node.
Yeah.
So why didn't you use multiple GPUs per node? Because was there a specific reason for it?
On Titan? So on our prior machine? Yeah. So Titan was the very first very large-scale GPU-accelerated machine. There were some smaller machines like Keeneland, which is run by the University of Tennessee, that were looking at, in that time frame, at multiple GPUs. I don't know the answer for that. My guess is it was considered too risky. This was the first step towards accelerated machines, and at the time, we didn't have application codes. When we procured Titan, we didn't have application codes that used GPUs. No one had done this before. So we still needed a strong CPU component for those codes that had not made that transition. So that would be my guess. Yeah. I'm around all day, happy to take more questions as you have them.